All right, we're transitioning to a new topic today, our last topic for the semester, geometric transformations. And to start with, let's actually define what we're talking about when we talk about transformation groups. So we're going to start with transformation groups. And we'll have our first definition. A geometric transformation we'll just call it a transformation for short, but it's a geometric transformation. Is, or F, we'll call it F first, is a set, I can't talk right, F of a set A onto itself is a map F from A to A which is both one-to-one and onto. I know not everybody's had exactly the same coursework thus far. Hopefully those two words are familiar to you, one-to-one and onto. Have you heard those in any other classes? And if so, where have you heard them before? I'm not going to make you define them, I promise, but where have you heard them? What classes have you heard those phrases before? Real analysis. Many of you are in that right now. Not everybody, but many of you. Where else? Discrete. Good. How about modern algebra? Usually comes up in there too. Another familiar word to modern algebra will come up very soon. Those were the three that came to my mind as being places you would have heard them before. Any others you can think of? No? Okay. So just as a reminder, sort of loosely defining, this means that each element of A is the image of exactly one element of A. Okay. So with that in mind, we're going to define another word, at least again, maybe not quite as completely as you do in modern algebra, but it is for modern algebra where you usually see the next word used. We're going to do a definition of the word group. A group of transformations specifically of a set A onto itself okay, so a group of transformations of a set A onto itself is a non-empty set S of transformations satisfying the following. First, for all transformations f and g in the set, f compose g is in the set. This is a closure property. I encounter and talk about this closure property with my elementary ed math students, like they're going to do elementary education. We talk about the fact that when we take two whole numbers and we add them together, we get another whole number. You take two whole numbers and you multiply them, you get another whole number. Those are closure properties. Closure doesn't happen all the time. It is a unique thing, because if you take two whole numbers and you subtract them, you may not get a whole number. Stuff like that. So this is saying that if you do a transformation followed by another transformation, it should still have been a transformation. Okay? All right, the second one is for all transformations f, g, and h in the set. If you do f after you do g and h, that's the same thing as doing f and g first and then doing h. Those are compositions. They're not really O's. My composition notation is looking a little bit large. But does anybody remember what property that is? Associative. Very good. So this is the associative property. The third one is that there exists an identity transformation in our set of transformations such that when you do that identity with another transformation, it's the same if you do that before or after the transformation, because it doesn't actually change the results of the transformation, and it works for all transformations in your set. And I already gave away that this is, of course, called the identity property. And I'll give you an example of one of these that you can visualize very easily in a moment. I have one more fact that it has to actually satisfy to be one of these. Number 4. For each transformation in your set, there exists, what is that? What do we call that usually? The inverse transformation, such that when you compose the transformation with its inverse in either order, you get the identity transformation. And of course, that's the inverse property.
What does I stand for?
Identity. The identity transformation. So let me just give you a quick sort of verbal description. I'm not going to write this one down, but you can picture it pretty well in your head. Imagine taking the Euclidean plane and rotating things. Okay, so you're not changing the size or the shape, you're just spinning it like a spinner on a game board, okay? So no matter where you spin things, obviously 2 spins back to back is the same thing as 1 spin, just of a different rotational value, right, angle measure. So it's got the closure property. It shouldn't matter what order you do the transformations in, right? So if I do a 30 degrees and then I do a 45 degrees and then I do a 50 degrees, it wouldn't have mattered if I had done the 50 and the 45 first and then the 30 afterward. The order doesn't make any difference. I still end up at the same location when I'm done after I spin. Okay, child on the merry-go-round. Hopefully that's kind of the picture you've got going on too, right? If I spin a 360 degrees, that would actually be the identity, correct? All right, you talk about spinning something 360 or back where you started with. And then for every transformation, every rotation that we do, there's another rotation that gets us all the way back to 360. So if I do a rotation that's 90, what transformation would I compose it with? What would its inverse be for a 90-degree rotation? A 270-degree rotation. or a negative 90-degree rotation if you're allowing negatives, depending on your perspective on how you define sort of some things. But there's always one that will get you back to where you were to begin with, okay? So that would actually be considered a group of transformations, rotations would. You need a little bit of restrictions because this is supposed to be that you have usually you're talking about a unique inverse. So we might want to restrict things to being rotations between 0 and 360 to make that work, right? Then we don't have to worry about negatives, or maybe there's an identity at 720, because there is, right? So we usually have to restrict it a little bit to make all the details work out, but that would be an example. All right, a collineation. T is a transformation on points and lines of a plane which preserves incidence. So in other words, i.e., if P is on line L, then the transformation location, wherever we've moved P to, T of P, is on the line T of L. And hopefully you can imagine that happening, that rotations do that, right? If I rotate the line, or it might be easier to think about the ray, which is just a portion of a line, but if you imagine rotating a ray around the origin, it's the spinner on the spin, you know, the points that are along the ray are still going to be along the transformed ray as well. So I'll actually write down another example. So let's take our collineation. It's going to be the real the Euclidean plane R2 onto itself, okay, just like my other example. What this one's going to do is it's going to take all the points x, y to the point x plus 2, y. Can you verbally describe to me what this is doing to our plane? Say it for me. How far? Yeah, it's shifting it to the right 2. That's all this transformation is doing. So this is a shift right 2 units. Does that make sense? If you take every line and you shift it right 2 units, then all the points that were on the lines also were shifted right 2 units. It preserves incidence, so it would be a collineation. So we're going to do a theorem. All right, I'm going to switch slides. Keep my proof for the theorem all together with the theorem. The theorem is the following. The set of all collineations of a plane forms a transformation group. So if you go back up to where we defined transformation groups, group of transformations up here. In order to prove this, we actually have to do 4 things. We have to prove that it's closed, we have to prove that it's associative, we have to prove that it has an identity, and we have to prove that it has an inverse for each element. Okay? So that's what we're going to do next. Our proof will consist of 4 pieces. The first one for closure. So we're verifying. Some of them are more a fact that we have to actually write down descriptions for, and some of them are just a stating a fact. So what happens when we compose 2 collineations? Will we get another collineation? Yeah, imagine if I take my points and I move them 2 to the right and then I move them 3 up. Is that still going to preserve incidence? Is it still going to have all the same details we had before? And it will. So composition of 2 collineations. Yields a collineation. So that one's good to go. The second one is the associative property. Associativity. This is actually an inherited feature of all functions with operation composition. The identity. So if we were thinking in terms of shifting things left, right, up, and down, like we talked about to begin with on this particular example, clearly if we map a point to itself, it certainly preserves incidence. So this clearly leaves, clearly the identity leaves things incident. And let's think about doing the inverse. Collineations are bijections. Means they go in both directions, hence have inverses. Since the point on the line L results in a transformed point on the transformed line, we know that the inverse transformation acting upon the transformation itself will result in the inverse transformation to the line, acting on the transformation to the line. And every point line pair can be viewed as a transformation point on the transformed line. All right, so collineations preserve incidence, right? That's what we defined them to be. If we get a little more specific about preserving other features, we actually have automorphisms. So an automorphism is a transformation that preserves incidence. So an automorphism is actually also a collineation because it preserves incidence. It also preserves betweenness. And it preserves congruence. So basically this is saying if the relationship, one of those relationships, holds before a mapping, then it holds for the images. Okay, so if one point is between 2 points originally, once it's transformed, it's going to be in between all of the transformed points that it was originally between as well. If you have a segment that is congruent to another segment and they're both transformed, their transformed lengths are going to have that same property. And an example of this, again with R2. So we're taking a function or a mapping that takes R2 into R2. And what we can actually do here is we're going to take what's called a dilation. So we take x1 or xy to 2x, 2y. So what is this doing visibly to an image? What is the image going to look like compared to the original one? It's going to look very similar image-wise, but what about its size? It's going to double everything, right? So it's going to enlarge it. So if you imagine going to a copier and putting 200% in the copier, the image looks the same, but it's twice as big as it originally was. Those of you who are education majors may have students who need that kind of thing happening on their tests in order to be able to read them. They have vision issues. So those are some features that preserve all the things that your original image was, it just makes them bigger. So visually for sort of a picture example, let me see if I'll do it here. How about medium? Let's go with this grid. So if I have a grid, let's go ahead and draw in the XY coordinate axis. And imagine drawing in a point. Let's just do 1 point. The point is at 0, 1. So where would that point be on the transformed axis? Where would that point go to? 0, 2, right? What if you had a circle and you had, okay, that's too thick, just a sec. Sometimes it's easier to draw things than to move them. So here's our circle of radius 1. What's that going to transform to? A circle of radius 2. That didn't do it. Let's try it one more time. I think that does it. Okay, so there's my circle of radius 2. What if you just had a line segment? Let's say you had a line segment. Let me change the color so that I can draw it in the same place. But let's say the line segment's right here. It's going from 0, 1 to 2, 1. Where will this line segment end up in our transformed image? Okay, well, one point you already know because it's already on our grid. This point right here transforms to here, right? Where will the other point, the end point, transform to? Where will it land? At 4, 2. So that would be over here, right? So we end up with that line segment, double the length it was before, but it's also in a different location. It's not just double the length, it's double the length and sort of elevated higher than it was before. You get both of those things happening simultaneously. That should feel a little bit different than the circle. The circle was expanding, but it was sort of expanding through its center, right? So it didn't look like it sort of moved, but the line segment did move because it wasn't actually centered at the origin to begin with. We've been working in my other geometry class on this idea of these dilations, and the dilations center where it's expanding from matters. It changes where the location of the image is. Maybe not the image shape and such itself, but the location of it. All right, I think that's enough of our examples to see what this is doing on this particular transformation. So this is the transformation F. Real quick note before I leave this screen. I'll write it over here. The set of all automorphisms automorphism is a long word. There we go. Of a plane also forms a group. We're not going to prove this one, but the proof is very similar to what we had had before with our collineations. Now, a non-example, that is, we're going to create something that is not an example of the, I'm still not saying that right. Our last example, with dilation, is not going to be an example of the following description. So let me get my backdrop to be my lines again. Okay, so another type of transformation, a descriptive type, a transformation T of the entire plane onto itself So all that sounds just like the last one. It was totally cool, transformation onto itself. But this preserves length, which preserves length, i.e. the segment AB that gets transformed into the segment A prime B prime. It's the same distance between those, the same length between those. So if these two are equal to begin with, where this is, I'm sorry, let me write this down, where A prime is the transformed point A, B prime is what I'm calling the transformed point B. So when this happens, this has a name. Does anybody know what it's called? Okay, this is called, your book calls it a motion. The other book that I'm using calls it an isometry. So an isometry preserves length. Our last example didn't do that, right? It doubled all the lengths. So dilations are not examples. They are non-examples of isometries. Oops. Okay. We're going to do a few proofs. Maybe just one. A few propositions, but one proof. So to start with, proposition 9.1. A. Every motion, or every isometry, is an automorphism. And part B of this same proposition is that the motions form a subgroup of the group of automorphisms. All right, so we're going to prove this one. So this is the proof for part A. That's actually the part we're going to prove. I don't think we're going to prove B today, just for A. Yep. So we're going to start with congruence of segments. For a motion T, if AB is congruent to CD, then we must show A prime B prime is congruent to C prime D prime. That's our goal. By definition, A prime, or AB, excuse me. No, I was right the first time. A prime B prime is congruent to AB. That's the definition of an isometry. And where we're told that AB is congruent to CD, that's given information. And then again, CD is congruent to C prime D prime because it's isometry. So we're done. Okay, so 2 definitions and the given information get us where we need to go on that fact. Segments are not the only thing that we would want want to be congruent to one another. What's another thing we might want to be congruent to one another when we're talking about preserving these ideas? Angles, and that's our next piece. So the second one we're going to look at is congruence of angles. So I wrote that. So congruence of angles. So let's suppose angle ABC is congruent to angle DEF. We must show angle A prime, B prime, C prime congruent to angle D prime, E prime, F prime. Let me start out this way. You guys seen WLOG? I'm not sure if I've used it this semester or not. WLOG, without loss of generality. Without loss of generality, assume AB is congruent to DE. And BC is congruent to EF. Okay? If they didn't have those features to start with, you could find another location closer that would actually have that feature, so that's why you can assume it without loss of generality. There's going to be a point that has that feature. Okay, congruent segments. Fantastic. Then, what we've actually created, in case you haven't been sort of keeping track visually, let me just draw it in here. Sketch, of course. Here's A, B, C. And actually, let me write it the other way. Our angle is going to be, no, that is what I wanted, ABC. And here's DEF. We have congruent angles here. That's where we started. And then AB is congruent to DE. And BC is congruent to EF. I don't have points marked on here, but pretend I did for a moment. There's A and C and B and D. So what do you think I might be headed towards since I've got all those now? Yeah, side angle, side. Those are triangles if we connected things well, like this, right? So then we actually have that triangle ABC is congruent to triangle DEF. And Hannah said side angle, side, which is correct. Hence, triangle A prime, B prime, C prime is congruent to triangle, D prime, E prime, F prime by side, side, side. Right, we have 3 pairs of congruent sides, so this triangles are going to be congruent as well. This gives us, giving us the angles that we were trying to show. Angle A prime, B prime, C prime, congruent to angle D prime, E prime, F prime. Okay, so we've shown the congruence arguments. We can use, when we've got angles and segments, we've got everything with congruence arguments. There's 2 other pieces of information that we're supposed to have the features preserved for an automorphism. flip back real quick to automorphism and tell me what another one of them is. Besides congruence, what else are we supposed to be preserving? Incidence, and what's the other one? Betweenness. So we're going to do betweenness next, and then we'll do incidence. So betweenness is our next one. So for betweenness, using the betweenness axioms that we have ourselves, B1 from before, B1 and B3, if P is incident with or lies on, I'm going to put it like this, P is on line AB, then either A, PB, so P is between A and B, P is before A, or P is after B, right? There's only 3 locations that it could be. Hang on. ABP is what I'm left with. And one of those 3 things happens. Oops, ran out of space. But betweenness is preserved. Oh, I'm sorry. I'm doing incidence. I'm so sorry. Let me relabel this and then it'll be fine. Mark out betweenness. I got off on my notes. I'm doing incidence right now. Ooh. That's what happens when you have windows and doors and sections and stuff. Okay, this is incidence. It's based on betweenness, which I haven't proven, but I'll go back and prove it, I promise, without sort of circular reasoning, I promise, okay? So we're going to assume we've assumed betweenness is true. We've proven it, even though I skipped it. But betweenness is preserved, yet to be proven, but I will. So P prime is on A prime B prime, that line. Okay, so that's incidence actually. Betweenness that I unfortunately skipped. So this should go right in here in order for it to make sense here. So we're going to start out by taking A, B, C, that segment or that length. So this is true if and only if AC is equal to AB plus BC. Okay, these are bidirectional, the if and only ifs, and this is true if and only if A prime C prime is equal to A prime B prime plus B prime C prime. All right, we're just transferring into the other part of this, the transformed part. And this will be true if and only if B prime is between A prime and C prime. So if I put them in the right order, we would be done. Yeah, I got the incidence and the betweenness labeled wrong when I was starting on. All right, is everybody caught up? Fabulous. Proposition 9.2, we're not going to prove this one. says the following. Every automorphism preserves angle measure. So we looked at how we sort of show angle measure being preserved in our last proof, and that actually works for every automorphism. Whenever I teach, and it's usually, there's a couple of classes, but college algebra is one of the locations where I teach the real number system. And Venn diagrams, I think, is a really good way to view the real number system. And it's very fitting for how we think about our development of numbers in our childhood. The first thing you learn about, and you learn to count starting with the number 1. And you don't learn 1, 1.5, 2, 2. You don't do that either, right? You learned 1, 2, 3. And then somewhere along the way, somebody expands your world just a little bit larger to include the number 0. Those are so the first numbers you start with are called the counting numbers, or the natural numbers. And then you expand your view just a little bit to include the number 0. You've got whole numbers. And then we talk about what happens when we have, a deficit to something, right? Like 3 minus 5. And our viewpoint expands a little bit more to include integers. So you have negative numbers. Even if not in a formal sense, maybe you learn fractions before you learn negatives. At some point you have this idea that there is a way to have not enough of something, right? You don't have enough something probably to buy the toy you want in the store or the candy. Anyway, but then you expand a little bit bigger and you introduce the idea of fractions, and then again we expand and we introduce the idea of irrational numbers, and then we get I and things like that. So our numbers keep getting bigger. You can use Venn diagrams for this idea very similarly. So we're going to start in the middle, give yourself some space here. In the middle we have our motions, or our isometries. So motions preserve size, right? They preserve size for us. And then we get something a little bit bigger, which we have just been describing a minute ago here, which are our automorphisms. Let me give myself enough space to write. Whoops. So the most narrowly focused thing are isometries, or our motions, okay? If we get things just a little bit bigger, we don't get all of the same properties. We include some other things as well, but we do preserve other facts, right? So what did we preserve with automorphisms? I didn't even spell it right up here. I left off the M and the S. There's an M and an S missing there. Sorry about that. What did we preserve for automorphisms? What were the things we just proved? There's 3 things we proved in our last proof. Congruence, betweenness, and incidence, right? So automorphisms preserve those 3 things. Do they have to preserve length? They don't have to. Could they? Sure, they could. They could, all right? And so, because it's a smaller, it's a subcategory inside. If we expand our picture a little bit more, it's where we actually began today. And we had, hang on, I'll move that in a sec. We had, what other type of transformation did we have? Where did we start? Collineations, exactly. So collineations don't necessarily have to preserve all of those things, but they did preserve something. What did they preserve? There's one and only one thing we wrote down. They preserved incidence. They preserved incidence. And then our biggest picture, which we'll draw on the outside like this, would be all transformations. And transformations in general, when we talked about them to begin with, The most we could kind of say about them is that they are bijections. So let's start on the outside of the circle, and I'll write the details in moving inside again. These are bijections. It means that they've got an identity and they've got an inverse, right? That's what it means to be a bijection, identity and inverse. And then if we focus a little bit more specifically, we preserve incidence. And then when we get a little bit more specific, not only do we preserve incidence, but we preserve incidence between this, I'm sorry, that's not right. What did I have here? Yeah, automorphisms. I was writing right. Yeah, incidence between this and what? Congruence. I'm running out of space, so pretend for a moment. And what did it mean? So motions preserve incidence betweenness and congruence and length, right? Size. They include that one as well. So we get incidence, betweenness, congruence, and I'll write length. You could write size, distance. We lose flexibility as we move inwards, but we gain structure. All right, I'm going to talk about one specific type of isometry today, and then this will be our last piece. This isometry is a reflection. Motion isometry. All right, so we're going to let R sub m denote the reflection of points across a line M called its axis. The image of a point P we'll call PM. Such that the point P with PM, the line or the line segment, whichever you prefer, that connects them, is actually perpendicular to M, and that location where it crosses M, right, its intersection point with M, identified as Q. That point is the midpoint of the segment PPM. So visually speaking, here's, whoops, but I grabbed it. Here's line M. And let's say that right here is point P. So the reflection across the line P would create a line perpendicular to M. It intersects at what point we're calling Q, and this distance is equal to this distance. That's what a reflection is. Okay, so a couple of notes about this. I think I have space here, actually. If you do a reflection twice, what happens? You get back to the same point. So we get back to the original, which means that's the identity. So the inverse of Rm is itself. Right? You betcha. Second note. The only fixed points what points do not get moved under a reflection? Q wouldn't. Why? Because it's on M. So any point on M would not get moved, right? Yeah. So the only fixed points are points on M. Three, lines perpendicular to M are left invariant, that means unchanged. The line itself is in the same location. So they're left invariant by the reflection Rm. So the line is in the same place, but only one point is fixed. What point? Right. The one on M is the only location, point that's fixed. Number 4. Reflections are isometries or motions. Which is exactly where I wanted us to end today, because that right there is what your homework is to prove that. You're like, oh, that wasn't what I was hoping for. Here's your homework for next time. Prove number 4 above. That's the first thing. The second thing, one problem, page 458, number 4. 2 pieces to your homework, and we'll end there.